In this tutorial, I'm going to give you a quick and complete introduction of Xcos. First, we're going to see what Xcos is. Second, we're going to have a look at the environment of Xcos. Third, we're going to see how we can launch Xcos from Scilab. Fourth, we're going to see what the palette of Xcos is. Fifth, we're going to analyze an Xcos block. Sixth, we're going to build an Xcos diagram. Seventh, we are going to see how to set up the simulation parameters for Xcos diagram. Eighth, we are going to run a simulation and visualize the results. Xcos is a graphical editor for constructing models of hybrid dynamical systems. Xcos models can be then assembled, loaded, saved, compiled, and simulated using the graphical user interface (GUI) of Xcos. The Xcos environment consists of an editor, a palette browser, and a compiler or simulator. Once Scilab is open, you have three options for opening Xcos. First is by typing Xcos in the Scilab console. Hit enter. As you can see, the palette browser has opened as well as a new block diagram file. Close this. The second option to launch Xcos is by clicking the Xcos icon in the toolbar. And the third option to launch Xcos is by clicking on Applications and then Xcos. The Xcos Palette is a library of predefined blocks that you can use. The blocks are organized in different categories based on the function they are performing. The recent used blocks category contains all the blocks that you have used in your previous projects. The continuous time system category contains blocks used for continuous time simulation. What does continuous time means is that your simulation is performed in a time step chosen by the solver. You're not having a fixed time step. In this category, the most used blocks are the ones for the transfer function. This one, you can also use an integral block, or you can use a PID block. Also, you have the state space block. The discontinuous category has block for discontinuous systems. For example, you can have a backslash block, a deadband, hysteresis. In the discrete time systems, you have blocks that are used in discrete systems. Those systems are calculated at discrete times. For example, every 10 milliseconds. The most common block used from this one are, for example, the delay block, which is this one. You can also have a discrete transfer function, which is this one. Or you can also have a discrete state space block. In the lookup tables category, you mainly have two blocks. You have the 1D interpolation block, which is this one, in which you have one axis and one map. And then you have 2D interpolation block, in which you have X and Y axis and a Z map. In the event handling category, you have blocks related to events. Events means that you calculate certain functions at certain events. For example, you may choose to have a if then else condition, this one. So for example, if the input signal is greater than 0, then I will choose to perform if action, otherwise I'll perform an else action. In the mathematical operation category, you have the basic mathematical functions. For example, you have the absolute value block, you have a sum, you have an exponential block, and some trigonometry functions. This is quite useful and you're going to use it a lot. In the matrix category, you have functional operations related to matrices. In the electrical category, you have blocks representing electrical components. For example, you have capacitors, you have diodes, you have inductors, and you also have resistors. In the integer category, you have blocks that are performing bitwise operations. For example, if you want to set a particular bit in a decimal number, you use this block. You can also have flip-flops, or you can have logical operations like AND or OR blocks. In the port and subsystems category, you have a block for a super function. This is a predefined function by the user. And also you have the input and outputs block, which apply to variables and also for events. In the zero crossing detection category, you have few blocks which are used to detect zero crossing. For example, if you have a signal which is crossing from positive to negative, when it's crossing zero, then you can generate an event. And this event can trigger the calculation of another block. In the signal routing category, you have blocks that are dealing with signal routing, which means you can multiplex signal or demultiplex. You can also have switches which perform the switching between two signals based on an input condition. In the signal processing category, you have two blocks. One is for quantization, another one is for sample and hold. Another important category is annotations. In this one, you have a text block which you can drag in your diagram and add additional text to explain what your diagram does. In the scenes category, you can have multiple scopes which you can use. The scopes are used to display results. These scopes can be used for one signal or for multiple signals, and they are time triggered. In the sources category, you find different blocks which can generate signals. For example, if you want to generate a constant value, you can use the const block. If you want to generate a sinusoidal signal, you can use this block. You can also use pulse width modulation signals, and also you can use data from the workspace using this block. The thermohydraulics category contains a few blocks related to hydraulic systems. For example, you can have a pressure loss block, you can have a pressure source block, or you can have a valve. In the user-defined functions category, you have a bunch of blocks which allows the user to define their own functions. You can also define a function based on a C code, or you can define a function based on Xcos blocks. In the palette browser, you also have zoom buttons which help you magnify or shrink the blocks in the view. For example, if I click on the plus scope, I can increase the size of my blocks. If I click on the minus, I can make them smaller and fit the window. Also, you can use the search box if you want to find a particular block. For example, if I want to find a gain block, I just type the name, gain, and then click on the search button. And I'm going to find all the blocks which are related to gain. To understand how an Xcos block works, let's take a simple example. Let's create a block diagram in which we take a constant and we multiply that constant by a gain. And then the result we are going to display it in a display block. So first let's add the blocks into our diagram. First let's use the source category in which we find the const block. There are two ways of adding this block to your diagram. First is by right-clicking on it and clicking on Add to Untitled. The second method is by left-clicking in the library and then drag and drop in your diagram. Now let's add a gain block. So we go to Mathematical Operations and we find the gain block. We do right-click, Add to Untitled. Now let's add a display block. So we go to Things and then we click on Affiche. Affiche, by the way, comes from French, I guess, and it means display. And then you say Add to Untitled. So we have all our blocks that you can drag, select, and then drag them into place. You can also click on the block and use your arrow keys to move the block up and down. Okay, and now the last block we want to use is a clock block, because this display block needs a trigger, a time trigger. So we go into sources and then we add this clock _C block. So let's click on it and then drag it into our diagram. Right. We have all our blocks. Now we have to add the parameters. So as you can see, the constant block has only one output, which is this one, because it just sends one value out. Okay, let's change that value to, let's say 4. So you double click on the block and then you have a dialog window open in which you can enter the value of the constant. So you just select this and say 4 and then click OK. Now we have our gain block. So we want to put a gain as 5. So we double click on it and then we change the gain setting 5 and then click OK. As you can see, the game block has two ports, an import port and an out port. So we want to connect the import to the constant, so you click on the constant output port, click, hold, and then drag. And then when you have the green square highlighted, then you release. Now you connected the constant block to the gain block. We'll do the same for the gain output. So click on it, hold, drag, and release it on the display import port. And now we connect the clock to the event port of the display, right? So now what is going to happen when we simulate this? Basically our value 4 is going to be multiplied with 5, and then we are going to see 20 in the display block. Okay, so now we can just click on start and the simulation will run, the operation will be done, and then we'll see the result as 20. One more setting you can change is go to simulations, setup, and you can change your simulation time. So final integration time means how long the simulation is going to be performed. In this case, it's set to 30 seconds. It's an exponential format, which basically means 3 times 10 at the power of 1, which is 30. So we want to simulate just for 1 second, because that's enough to do our multiplication. Say 1 and then click OK. You run again, have the same results. If you want to see that it works, just change the game block, let's say 10. Okay, and then run again. And you have 40. Let's take a more complicated example. Let's try to integrate a differential equation into Xcos. Before we do that, I want to write the differential equation in order to be easier to understand what I'm building in terms of block diagrams. So first of all, what I'm going to do, I'm going to double click on my untitled file. When you double click, as you can see, you automatically get a text. You click on the text, double click on it, and now you can edit. So what I'm going to do, I'm going to add some latex code, which is going to contain my differential equation. To write latex code into the comment, you have to use the $sign. So I'm just going to type $, and in between the dollar signs, I'm going to type the latex equation. So I'm going to write fraction let's make this let's try again. Write some text. I just want to make this a bit bigger so you can see what I'm typing in the equation. So I'll just say $, and then in the middle I'm going to say fraction. Okay, and then I say dy over dx equals x at the power of 2 minus 3. Okay. So you see, when you click out of the text, the latex code is compiled into a symbolic equation. So this is my differential equation, which I want to solve. Now I know that the analytical solution for this equation is, I'm going to add another latex text, so $, and the analytical solution is y of x equals fraction x at the power of 3 over 3 minus 3 times x. Right. So let's zoom out a bit. So I have my differential equation on the top, and then I have my analytical solution. I'm going to add a bit more text to say differential equation. And then here I'm going to say analytical solution. Okay. Now I have these. So these texts are just for giving more information on what we are going to do. They don't have any role in the simulation. So basically now I'm going to try to create a block diagram which is going to solve this differential equation. Misspelled analytical, so now it's in the correct form. Now if you want to have the solution of this differential equation, and you want to see how you get from the differential equation to the analytical solution, you can use this link, which I'm going to write it there. So say reference. Right, so zoom in a bit. So at this web address, you can find exactly how you get from the differential equation to the analytical solution. Okay. Now, what we want to do is we want to solve this differential equation with Xcos, and we want to compare the results of the differential equation with the analytical solution. So we are going to use blocks which are solving this differential equation. So how we start is by adding an integrator block, because the integrator block will basically integrate the right hand side of the differential equation. So we go to continuous time systems, and then we use the integral underscore f block. So you right click on it, say add to untitled. Now you can leave it as it is in terms of size, or you can make it a bit smaller. So I usually do this, make it a bit smaller because I don't want to occupy too much space. Right. Now I want to integrate x at the power of 2 minus 3. So x is the time in this equation. So I'll go to sources, I'll scroll down, and I'm going to choose time. So click on time, add to untitled. So this is x. We can also imagine that x is t. So the equation will become dy over dt equals t squared minus 3. But let's keep x. Okay, so the output of the clock is x. And now I want to take x and make power of 2. So now I'm going to go to mathematical operations, and I'm going to scroll down, and I'm going to use the power block, this one. So say add untitled. Again, you can make it a bit smaller, the block. So now I want to change the exponent. Instead of 1.5, I want to have it 2. So double click on it and then change 1.5 to 2. So how this works is the value that goes in is the variable u, and u is going to be squared, and then is going to be sent out. So I'm going to connect the clock block with the power block, and now I need to do minus 3. So I'm going to add a new block, which is summation, this one. Right click on it, add to untitled. So I need to have a plus and minus. So as you can see, by default I have first import as plus and second import as minus. If you want to change that, to double click and then you change the signs here. So for example, if I put 1 and 1, I'll have 2 pluses, which means this import is going to add it to this one. But since I want input 1 minus input 2, I have to have minus for the second input. So leave that at minus. So now I'm going to connect the output of the power block to the first input of the summation, and I have to add a 3. So I go to sources, then constant. Again, make this smaller a bit, and then double click and say 3. And then click OK. All right, so just connect this. So now I have the right hand side. So I have x at the power of 2 minus 3, and I want to integrate. And then the output of the integration block will be y. Okay. So to display and visualize y, I can go into sinks and I can choose a scope. Let's say this one, see scope. So add to diagram, and I'm going to drag it there. Okay. I just realized the analytical solution has a mistake in it in the equation. So if you double click on the equation, then instead of dot you put c dot, you'll have the right answer. So in LaTeX, dot means like a derivative, and c dot means multiplication. To visualize the result of the differential equation, we also have to put a event clock which will trigger the scope. So we go into sources, and then we put this clock with the red circle. So the difference between this block and this one is that this one will generate time, the simulation time, and this one will generate events or samples. So we use the sample clock to trigger sample blocks, the ones which have this red import, and then the black one are just generating simulation time. Okay, I'll just drag this a bit down, and I will connect these two ports. Right, so now we have a complete block diagram which will solve the differential equation. What we have to do now is click start. After you click start, you'll have a graphical window pop, and you'll see the result of the simulation. As you can see, the axes are not fit for purpose. So for example, x-axis, which is the simulation time, it's too long, so it takes 30 seconds. We might want to reduce this to about maybe 6 seconds. And also we want to change the y-axis. So to change the display, we have to go into the scope block and change some parameters. So I'll put this aside. I'll double click on this block. So as you can see, you have several options. So we want to change the y min and max. So we want to put the minimum y up to -5. Just put here -5. And the maximum is 15. We leave it as it is. And then we want to change also the refresh period. So instead of having 30, we'll have, let's say, 6. And then the buffer size, we'll put it also 6. So the refresh period means if the simulation time, for example, is 100 seconds and you have a refresh period of 30, every 30 seconds the plot will be redrawn. And then buffer size means how many points for the simulation I'm going to save. So 6 means I'm going to save 6 seconds, and I'm going to have a refresh period of 6. Usually I put these two will match, so you'll save as many points as you want to display once. So you just, these are the settings we want to put, and then we click OK. Now I'm going to go into the simulation setup, and I'm going to simulate only 6 seconds. I'm going to close this and then run again. So now we have a better view of the result. So you can see it starts from 0, goes to minus 2.5 and then goes back up to above 15. Now, how do we know that the result is correct? One way to do it is to compare this result with an analytical solution, because we have the equation of the analytical solution. So we are going to add some other blocks which are going to calculate this equation. So we close this, move this down. So what do we need? Well, we have the time, which is x, but now I have to do it at the power of 3. So I'm going to copy this block. So just select it, Ctrl C and then Ctrl V, drag it down. But now I want to have power of 3. So I double click here and change the power to 3. Okay. Now I want to connect this signal, the power block input, to the time. So I'll just click here, hold, then release, and then click again, move to the left, click again, and then click on the output of the time block. When it becomes green, means if you click, you're going to connect the line. So I'll click there. So you see this orange point is a connection point, which means that the signal coming out from the clock block is going to be split two ways, one going to the power of 2 and then the other going to the power of 3, right? So now I have the power of 3 calculated. Now I want to divide by 3. There are two ways of doing it. One is by using a gain. So I'll go to mathematical operations. I will use this gain block. And I'm going to multiply by 1 divided by 3. Multiplication with 1 divided by 3 is the same as dividing by 3. Okay, so I'll just connect these two blocks. The second way of doing it, you could go to maths as well, and then you have to choose the product block, where you have function of the settings. You can have basically a division. So you have input number 1 is going to be divided by input number 2. But I decided to use a gain block. Now I have this done. So x at the power of 3 divided by 3. Now I have to do minus 3 times x. So what I'm going to do, I'm going to use the same summation block. So I'll just select this one, Ctrl C, click, Ctrl V. This becomes the first input. And now I have to subtract x times 3. So I'm going to use another gain, but this time with 3. So the input of this gain block is going to be x. So click here, drag, release, and then click again. So I have x times 3, which is this part, and this will be subtracted from this one. Right. So now I have both the differential equation is calculated in the upper part, and then the analytical solution is calculated in the lower part. So now I want to use both signals and display them on the same plot to see if I get the same result. So what I'm going to do, I'm going to multiplex those two signals. I'm just going to delete this line because I want to multiplex the output of the integrator block with the output of the summation block. So I'm going to go to signal routing, and I'm going to use a MUX block. So move this here. And I'm going to connect these two signals. So multiplexations means that I'm going to basically add both outputs in the same signal. So I'll have a array then in the output of the multiplication instead of scalars every sample point. Yes, if you have diagonal lines, you can click on these control points, the green ones. You can click and move left and right, and you can put them into different places. So I'll just move this block a bit there and then move this point to the left. I have a straight line. Just want to make it a bit prettier, so I'm going to delete this line and connect it again. Right. And now these two, I'm going to put them in the scope because I want to have both of them plotted on the same axis. Now let's change the simulation parameters. But before we do that, save your file. I saved mine, but you can save it too. So in order to save it, go just to File, Save As, give it a name, let's say my differential equation, and then click Save. To change the simulation parameters, click on Simulation and then Setup. You can see that a new window opens in which you have several settings. The solver kind is the numerical method used to solve your differential equation. By default, we have this Newton method, but if you click on it, a drop-down list will appear and you'll have different options for different numerical methods. For this example, we are going to leave it on Newton, but we're going to do a small change and we are going to change the relative tolerance to a smaller value just to see the difference between the analytical solution and the numerical solution. So we'll change this to e at the power of -2, which basically means that the relative tolerance will be 0.01. So click OK. Now we're ready to run our model. In order to run the model, go on the Start button and click on it. After we run the simulation, a graphical window will appear, which will contain two curves. The black one is the differential equation and the green one is the analytical solution. As you can see, starting from 0.7 seconds onwards, the solutions are a bit different. So we can just maximize this for a better view, which shows you that there is, because we increased the relative tolerance, the numerical method will have some errors while solving the differential equation. That's why there is a difference between the analytical and the numerical one. If you want to improve the accuracy of the integration, so close the plot, go back to simulation, setup, and then put the relative tolerance back to e -0.6. Click OK. Now you can run again. As you can see now, the two curves overlap each other, which means that the solution given by the numerical integration is very, very close to the analytical solution. For you to get better, try to use another differential equation, integrate it, and compare it with its analytical solution.